Let's repeat what we saw in chapter 16 on enhancing soil carbon. Okay, we said soil carbon sinks can be divided into three categories: those that slow the emission and allow the carbon to accumulate. So if more carbon is being put in than is being emitted, being lost, then carbon accumulates. Those that increase the rate of carbon capture by the plants, so it's related to the afforestation that we just talked about with all its caveats, and those that use amendments to stimulate plant growth, increase carbon storage, and reduce emissions in other sectors. So we talked about how fertilizers and amendments are very different. Fertilizers are directly trying to add nutrients to promote plant growth, whereas soil amendments are slower processes where you are trying to improve soil health, soil quality, reduce soil pollution, soil loss, erosion, other things, and increase their potential to stimulate plant growth. So those we have to still remember. And looking at soil organic carbons in central US, the conventional tillage from early in the 20th century, whereas immigration and populations began to increase and food production began to increase as well, including for export. Conventional tillage with crop rotations, tillage between cropping and so on and so forth, kept degrading the soil organic carbon in the soil. So there is the loss again in gram per meter squared over the top 20 centimeters of the soil, and there is a loss going from about 7,000 grams per meter squared down to about half of it by the 1950s. And then we had reached 54% of the 1907 values of soil organic carbon with this estimate. And then advent of reduced tillage from the 1970s, or at least the stopping of the degradation of SOC from the 1950s after the war, has started to put back some of the SOC into the soil. But we are still at 61% of the 1907 value. Obviously, this includes lots of other processes as well, and not just agriculture, I'm sure, but this is more directly related to SOC due to tillage practices. So reduced tillage use things like no tillage planting, cover crops that we talked about, especially legumes of the pea family, which are good for sequestering nitrogen into the soil, contour plowing to reduce erosion and runoff, and more recently there are precision agriculture, climate smart agriculture, and so on. Okay, we won't spend too much time because we had a whole chapter on soil carbon already. Moving on to biofuels and carbon dioxide capture, which is referred to as BECCS, bioenergy and carbon capture and sequestration. This is showing an example of the smoke coming off a pile of burning leaves, which carries lots of volatile organic compounds being cooked out of the biomass. Okay, so there are ways in which actually this can be done as a gasification, where or other methods of chemical reactions, which can condense the volatile organic carbons to form a biofuel. This is mentioned here is pyrolysis, which is a high temperature reaction process which doesn't allow the volatile organic compounds to just escape into the atmosphere, right? So CO2 produced during fermentation and anaerobic digestion or in landfill emissions can also be captured and reused, but this obviously adds cost. Pyrolysis, of course, also costs something. So it's always a matter of how much CO2 can be drawn down, how much it costs, and how we would pay for it, in addition to making sure that when you include the electricity and heating that's required for capturing fuels from biomaterial, stock material, that we are net negative in the end. Okay, so this is an example I took from the Global CCS, Carbon Capture and Sequestration Institute. BECCS, that's the terminology mentioned, bioenergy and carbon capture and sequestration. So if you just look at the schematic, there is atmospheric CO2 being captured by plants of any sort, either grown specifically for biofuels like switchgrasses and Jatropha in India and various other species which have high content, or we can go to cellulosic when the technology becomes perfected. So either way, they provide biomass, so they are energy crops or residues from farm activities or waste from food production or domestic waste and so on, which is going to produce biofuel, bioenergy combustion or biofuel conversion for various uses like heating, transport, power, and industry. At source, CO2 is captured and transported and then stored somewhere. We will see what are the problems and what are the potential for deep geologic formations, and what are the methods that ensure that they will stay there for a long time, because you don't want them to leak after you put them somewhere in the ground, right? So gasification and syngas production is another method where biomass is combined with water. Obviously that also has water in it, oxygen and air. So this is a very high temperature process where gasification happens. There is some pre-treatment involved, like drying and grinding, which is why H2O is added here for the processes. And gas cleaning up involves removal of particles, tars, inorganic impurities. There is some conditioning of the gas involved in reforming water gas shift, hydrogen separation, which is the fuel you most want in terms of high energy density. CO2 separation, because you want to remove CO2 and not let it escape. So this produces what's called syngas or synthesis gas. So this is a cartoon of the synthesis gas from the Syngas Chem website. So things like gas, oil, coal, and biomass go into steam reformation that we talked about for extracting H2O, if you remember, and gasification or partial oxidization. So the methods by which syngas is produced, which is like a intermediate for producing other things like H2, synthetic fuels, and methanol, that is an additive to gasoline, right? So this is the process of gasification and so on. So these are technologies that are available. Then the question is the cost, the benefits, the net CO2 removal, and the potential for sequestering the carbon that's been removed, or use that CO2 into products. Not like putting it into soda, because if you put it into soda, it's going to be released again. But to hide it somewhere, sequester it away. That's the key.